Hi, welcome back to Chemistry. You're here with Mrs. Mays, and today we are talking about the meaning of a balanced equation. Of course, you already know about the law of conservation of mass, but let's make this more practical. Balanced equations are like recipes. Take, for instance, the recipe for a cheese sandwich. To make a great cheese sandwich, I need 2 slices of bread, a slice of cheese, and then I have 1 cheese sandwich. So could you predict how many cheese sandwiches, as defined by the recipe in this picture, you can make if you have 6 pieces of bread and 4 slices of cheese? Well, of course we could, because every sandwich takes 2 slices of bread. Then that means you can make from 6 pieces of bread at least 3 sandwiches. Well, at most 3 sandwiches, that is. Since every sandwich only needs 1 slice of cheese, then for the amount of cheese that we have, we could make 4 sandwiches. But of course, we'll never get to 4 sandwiches because we only have 6 pieces of bread. So the most we could ever do is here, 3 sandwiches given these amounts. What if I needed to make 14 sandwiches? So if I need 14 sandwiches, then how many slices of bread will I have to have? Well, if it takes 2 slices of bread per sandwich, then I need 28 slices of bread. Really, this isn't rocket surgery. Chemistry and stoichiometry is a lot like cooking. If you know your recipe, you can figure out all the rest. So, of course, we know chemistry is not really about bread or cheese, although they are made of molecules. But instead of talking about slices of bread or pieces of cheese or whatever, chemists talk about moles. Not like the furry critters. That's a gross-looking sandwich. Moles measures the amount of stuff. So a chemist will use moles in their recipe or their balanced equation. Here's another kind of recipe. Suppose we make tricycles. And at our tricycle factory, we have to have, 1 seat and 1 set of handlebars and 3 wheels and a frame and some pedals. And then we can make a tricycle, right? Well, suppose we get a shipment with 400 seats. Well, then I can make 400 tricycles, right? Only if I have enough wheels to put on those. So if I have 600 wheels and each tricycle requires 3 wheels, then the most tricycles I can make is 200. I'll never get 400 because I'm going to run out of wheels before I run out of seats. So we know what kind of recipe we need for building a tricycle. We can make some predictions here. Now we know that amounts in chemistry are measured in moles. And here's the thing. When you run out of moles, your yield will be limited. Just like running out of tricycle seats or running out of wheels. We can't make any more tricycles if we don't have the parts we need. And in chemistry, we can't make more products if we run out of our reactants. So here's a balanced equation. Let's talk about how this is like a recipe. So basically what this says is that for every 4 ammonias we have and 5 oxygens, we can make 6 waters and 4 nitrogen monoxides. That's our recipe. So chemists would say for every 4 moles of ammonia, 5 moles of oxygen are required to produce 6 moles of water and 4 moles of nitrogen monoxide, because we measure things in quantities called moles, which represents 6.02 times 10 to the 23 molecules, or atoms of something. Stoichiometry refers to the relative quantity of moles because meter means to measure and stoikos means amount. So we're measuring amounts. It also refers to calculations that make use of mole ratios from balanced chemical equations. So let's make some predictions. if I have 0.176 moles of oxygen. So here's my starting amount. I'm going to underline that. Then how many moles of water would be produced? Well, I'm going to set this in my T table so I can make sure that I get things to cancel properly. See, I want moles of oxygen to go away, and I want it to become moles of water. So I'm going to put that in what's called the mole ratio. That means I take the amounts from the balanced equation that tells me what my recipe says. My recipe says I get 6 waters when I use 5 oxygens. So those amounts go into my T table, and then we do the math. We take the top times the top and divide by the bottom. So I get 0.211 moles of water if we start with 0.176 moles of oxygen. And of course you'll round to 3 sig figs because that's what we started with, and put a box around your answer. Don't forget to label what kind of moles we're dealing with, because in this equation we have 4 different kinds. So we couldn't just say moles, we have to say moles of water. Moles of what? Let's look at another example. If I start with 17 moles of water, then how many moles of nitrogen monoxide can we get? So here's my starting place, and here's my target. Since moles of water is on top, I'm going to put moles of water on the bottom in my next step and turn it into moles of nitrogen monoxide up here. So what's my mole ratio? The number for moles of NO is a 4, and the number for water is a 6. So my mole ratio is 4/6. Then I take the top times the top, 17 times 4, then divide by what's on the bottom, and I get 11.3333, but I only get to keep 2 sig figs, so let's call that 11 moles of nitrogen monoxide. Put a box around your answer because that's the way I like it. Now we're starting with 1.9 moles of ammonium. The question says how many grams of water are produced. So we'll put 1.9 moles of ammonia in the starting line of the T table. And since moles of ammonia is on top, then that's got to go on the bottom in the next step. What number in our balanced equation goes with ammonium? 4. So 4 moles of ammonia, and I want to turn it into moles of water. And that number comes from this piece, 6 moles of water. But we're not done yet because I have moles of water, but now I need grams of water. So go back to your mole roadmap if you need to. To turn moles into grams, I need the molar mass. For every 1 mole of water, how many grams will there be? Well, oxygen weighs 16 and hydrogen weighs 1 each, and there's 2 of them. So that means my water is 18 grams per mole. So now if you look, moles of ammonia cancels, and moles of water cancels, and we're left with grams of water. So I take the top times the top and then divide by the bottom. So 1.9 times 6 times 18 divided by 4 times 1, which is 4. And I get 51.3 grams. How many sig figs? Only 2 sig figs, huh? All right, so 51 grams of water it is. For the next example, suppose that we started with 0.3 moles of water. The question is how many grams would be required to get that much water produced. So we start with our given on the line. And since we have moles of water on top, that's definitely going on the bottom in the next step, so I can cancel that away. And we want to turn it into oxygen. So there's 5 oxygens for every 6 waters. We'll put the mole ratio in our T table next. And now I have moles of water on top, and I need to get rid of it. Let's figure out the mass, or the grams, of just 1 mole of oxygen at a time. But this is oxygen that's diatomic, so it's 32 grams, not just 16. There's 2 atoms of oxygen in each molecule. Okay, now multiply the top times the top, and then divide by the bottom. And I got 8 grams even. 8 grams of oxygen. I only get to keep 1 sig fig anyway. In our last example, we're going to turn 12 grams of oxygen into grams of nitrogen monoxide. So start all the way over to the left because I have an extra step to do here. If we start with grams of oxygen, I have to turn it into moles first. So with any chemistry problem, go to moles. If you can figure out how to turn your amount into moles, that's a great place to start. So when in doubt, go to moles. Now let's see, I have grams of oxygen on the top, so I need grams of oxygen on the bottom, and I just said I want to turn it into moles. Let's do the grams of just 1 mole of oxygen at a time. So we just figured that out. Oxygen is diatomic, so it's not 16, it's 32 grams of oxygen for 1 mole. And now I need to turn the moles of oxygen into moles of nitrogen monoxide because that's what the question is asking for. So we'll put moles of O2 on the bottom, so it will cancel. And I want to turn it into moles of NO, so that goes up on the top. And then I get these amounts from the balanced equation. 5 goes with oxygen, and 4 goes with NO, nitrogen monoxide. Now, moles of oxygen has canceled away. Grams of oxygen has canceled away. I have one more step to turn moles of nitrogen monoxide into grams of nitrogen monoxide. So for 1 mole of NO, how many grams are there? Let's add the mass of nitrogen plus the mass of oxygen. Oops, just 1 oxygen, so 16. 14 plus 16 gives me 30 grams per mole. Then I multiply the top times the top, so 12 times 4 times 30. Then divide by the bottom, 32 times 5. Be careful in your calculator to divide by the entire bottom, not just one piece of the bottom. And I got 9 grams of NO, but since I started with 2 sig figs, I want to use 2 sig figs in my answer, so I'm going to call it 9.0 grams of nitrogen monoxide. And that's the meaning of a balanced equation. It's a recipe that tells us how many moles to mix together so I can get what I want. Now you have a job to do on your notes. You need to find the total moles of water that are on the front and back of this page for your notes. Then calculate the molecules of water, the grams of water, and then the total atoms altogether. See you in class.